Hi everyone, this is TJ Bowman, co-author with Eric Hansen of our paper, Improved Vector Pruning and Exact Algorithms for Solving POMDPs. Before we discuss anything else, let's define the problem. Given a set U of n-dimensional value vectors, prune all dominated vectors. So what is a dominated vector? Well, a vector W in vector set U is dominated by the other vectors in U. There is no n-dimensional probability distribution B for which the value of W at B is greater than the value of any other vector in U at B. Let's look at the picture to illustrate. This graph shows two-dimensional vectors. The x-axis is the probability distribution of being in either the first or second state. Now consider the red dashed vector. This vector is considered dominated because there is no belief for which the vector has a greater value than all other vectors. Another way to think of this is by considering the blue line. This piecewise linear and convex upper surface is formed by the vectors that aren't dominated. If a vector isn't needed to define this surface, then it's dominated. As you can see from the table, the vector pruning problem is relevant in many different contexts, but we focus specifically on its role in exact algorithms for POMDPs in our paper. For those who don't know what a POMDP is, a POMDP, or partially observable Markov decision process, models a planning problem with a set of hidden states, a set of observations, and a set of actions. The process unfolds over a sequence of stages, and at each stage an action is taken that results in a reward, a probabilistic transition to the next state, and an observation. The common objective is simply to maximize the expected sum of rewards at each stage. One such problem explained in our paper is the hallway problem shown here. In this example, the agent is trying to reach the star without complete knowledge of their current location. They instead rely on observations about the surrounding walls. The original vector dominance test relies on a subroutine that solves the linear program in the blue box. The details of this linear program are described in the paper, but notice line 2 in particular. We are generating a constraint for all the vectors in U, and each constraint has a variable for each state in S. This means that the dimensionality of these linear programs depends on both the number of vectors in U and the number of states in S. So why is this linear program so important? The typical size for these linear programs is often massive, using over 100 states and more than 10,000 vectors. In addition, we solve a huge number of these linear programs. These two factors cause such a major bottleneck in solving POMDPs that solving these linear programs accounts for as much as 95% of the running time, especially for larger problems. This bottleneck was recently addressed in part by Walraven and Span. They showed that instead of solving one large linear program, a technique called Bender's decomposition can be used. This technique solves a sequence of small linear programs where a new constraint is added each iteration until either the vector is shown to be dominated by the linear program returning a non-positive d-value, or the vector is shown to be not dominated by the linear program returning a positive d-value, and where d cannot be further decreased by adding another constraint that optimizes the belief distribution. The result of applying this technique is that each linear program has only a small fraction of the constraints it would normally have using the original technique. And this brings us to the first contribution of our paper, an early termination test for Walraven and Span's algorithm. Their algorithm continues to add constraints until the vector being tested for dominance is shown to be dominated, or until the objective d is optimized. Our improved algorithm similarly stops when the vector is shown to be dominated, but rather than continuing to optimize d for non-dominated vectors, it terminates early when the vector can be shown to be the best possible vector for the belief state b. This subtle change still categorizes vectors as dominated or undominated correctly, but with substantial speedup. Our second and primary contribution of our paper is inspired by two main insights. The first is that the number of non-redundant variables in the solution of the linear program is equal to the number of non-redundant constraints. This suggested that a similar heuristic to the one used by Walraven and Span could possibly be used to quickly find the non-redundant variables as well. The second insight is that we can indeed quickly find the non-redundant variables using a Bender's decomposition of the dual linear program. The details of both of these insights are explored more in our paper. The resulting new algorithm starts with a linear program with only two variables and constraints, and adds a variable or constraint each iteration until the vector in question is determined to be dominated or not dominated. The result is that the linear programs have a greatly reduced number of variables in addition to a reduced number of constraints. As a foundation for our algorithm, we detail and prove the following theorem in our paper. Rather than explain it now, though, we simply note its existence here to further solidify the point that we can detect whether or not a vector is dominated by solving surprisingly small linear programs. To give some perspective on the reduction in linear program dimensionality, consider again the hallway example shown before. It's quite clear that both the Walraven and the early termination algorithms yield a significant reduction in the number of constraints from the original algorithm. But notice that they still both solve linear programs using all of the original 92 variables. Our algorithm yields a similarly small reduction in the number of constraints, but it also reduces the number of variables to a small fraction of the original amount. Of all these algorithms, our new algorithm winds up solving more linear programs than the others, but each linear program solved is so small in comparison that we still see significant speedup, as we'll see in the next slide. It's quite clear from this graph that our algorithm represents not only a significant improvement on the original algorithm, but also an improvement on Walraven's algorithm, even using our improved early termination test. We saw similar results on other problems from the POMDP literature as well as randomly generated vector sets, and those details are all described in the paper. In conclusion, our algorithm now stands as the fastest method for pruning dominated vectors. In future work, we plan to investigate heuristics to reduce the number of linear programs solved. We also plan to investigate our theorem's application in other exact algorithms for POMDPs, high-dimensional convex hull algorithms, and other contexts as well. Thank you for your time, and I hope you enjoyed our presentation.